Hello, everybody. This is going to be our recorded video lecture on threads, executor services, and quicksort. So let's just dig into it. First of all, I'd like everyone to do the quiz. So if you follow this link right here, you'll find our quiz. It gives the Java docs for a couple of things that are now standard in Java. First of all, there's interface future. It has some method get. It waits for the waits if necessary for the computation to complete, and then retrieves its result. There's also something called an executor service, which has a bunch of methods, including two important ones right now. Invoke all, which takes a bunch of bits of code. It's in this callable interface. That basically, there are a bunch of tasks or code that you want run, and it will invoke all of them and return it. So let's see, executes the given task, returning a list of futures holding their status. And the results when all complete. Future is done is true for each element in this requirement. There's also a function called submit, which takes a single task and returns a single future. This submits a value returning task for execution and returns the value function representing a future, also known as a promise, representing the pending results of the task. The future's get method will return the task results upon successful completion. If you would like to immediately block waiting for a task, you can use constructions of the form to submit it and then call get, and that'll give you the result. So given all this documentation, what I want you to do is imagine that invoke all did not exist and all you had was future get and submit. I want you to write do-it-yourself invoke all. So just write the pseudocode for that. I've written a little starter point for you here, where you're going to take in some executor and a bunch of tasks. And I want you to assume invoke all doesn't exist and just build it out of the other components. So with that, pause the video, please, and write your code. Okay, we're back. And so let's sort of talk about how to approach this. So let's write this really quickly. So first of all, I have this do-it-yourself invoke all here. And it takes both an executor service and some set of tasks that I want to call. So the first thing I'm going to need to do is create a list. So a list of futures of type T. And I'm going to call that the futures. And what I did on this is you can create just an array list. It fills in the type, but I like to let it infer that from me. And if I just return futures, obviously this is not correct, but at least it compiles. We can start there. Well, let me bring that back. One bonus thing I'll say here is that array list takes a bonus parameter called, this is totally optional, of what capacity you would like it to be. So if I tunnel in here, it takes an initial capacity. It feels like we know the exact size of what we're going to put in here, right? We're going to end up creating a future for every task, so why not just tell it up front? This is not a performance concern. I'm not really building it this way to, obviously you don't need to put this in your pseudocode, but just as an aside while we're here, it's kind of nice as a bit of expression to the person reading your code. Oh, by the way, I know exactly how big this is going to be. It's going to be this big. When we're done here, this future size will be 0. Like it's not putting stuff in there, but it's just giving a little hint to the array list. This is how big I would like you to be to start. And since we know, why not? So now let's say for each callable, and that's going to be a callable type T. Oh, let me call that a task. In the tasks, right? Those are the pieces of code that they want us to run. Let's just futures.add, and I'm going to take my executor service and submit that task. That will create a future and put it in there, okay? And so I want everyone to pause the thing in a moment. This code is not correct. Why not? I want everyone to look at it and figure out what is missing from this code. Okay, and we're back. And so hopefully a lot of you have seen that going back to our documentation here, rather critically, invoke all says, returning a list of futures holding their status and results when all are complete, right? Future is done will be true for all these things. So what I need to do is I need to correctly build something that mimics invoke all. as I need to just make sure all these features are done. So this is going to be a little, before I leave, for each feature in futures, right? I'm just going to call future.get. Taking the result and just throwing it on the floor, right? Someone on the outside will undoubtedly be interested in these results, right? But I just need to call get, which has this nice side effect of, so let's go over here. If you look, I need to just call get because which has this nice side effect of waiting for it to complete and returning the results. So I'm just saying, let's just use that for that. Okay, and so hopefully that makes sense to everybody. Let's sort of press on a little bit. The prep for next time is going to be scan. This is a fundamental primitive in parallel programming. One of the things that I think we fail a little bit in this class is we have a little bit too much programming and not enough parallel specific programming. This is not one of those cases. Scan is a fundamental parallel primitive, and it's a useful thing. And so I want everyone to watch these videos. The first one is on Hillis and Steele scan, which I feel like is it's a very nice, more understandable algorithm. We're going to have a required studio on Hillis and Steele scan for next time. And so how I want everyone to do is everyone's going to watch this video. And if everything makes complete sense to you after watching Hillis and Steele scan, for those people, I want you to watch Blaylock scan, which is going to be a work efficient version of the scan. This is going to be an optional extra credit portion of the program. So everybody who doesn't understand Hillis and Steele scan, I want you to watch it twice. Everyone who's got Hillis and Steele scan after watching the first time, go ahead and watch the Blaylock scan prep. Okay. And with that, let's press on to introducing and getting ready to do our next lab. Okay. And before I start, I just want to say, I want to bring everybody back and have everybody recall our merge sort data race. If you recall, a fair number of people make this mistake. And the mistake is that, merge sort was going to sort in place the shared mutable data. And our plan was that no one was going to, everyone was going to go from only work on their range. And that's how it was going to be a data race. And like people just mistakenly put in merge sorting the whole thing at the bottom. And I'm just going to give the heads up that some people every semester make this mistake again on Quicksort. I don't take this as a great point of pride from my being a teacher that I can't iron this out, but I want to give you the alert up front to be just wary that the same potential problem where we're going to build Quicksort, where we're going to mutate, we're going to sort everything in place and mutate some shared mutable data. And the plan is going to be that we all work on our respective ranges. And just be on the lookout for this possibility where you're going to make this mistake, but for Quicksort. All right. With that, let's introduce Lab 4, which is going to be in threads and executors, sort of the getting away from async and finish, seeing a little bit how async and finish is built for our V5 algorithm. And a lot of students kind of like this, being able to build in something more standard in Java. And again, a lot of this course owes a great deal of thanks to Finn Wojcik, who's one of your fellow students now about to be an alum, who contributed greatly to the creation of this course. Okay, so let's talk about the motivation here. Like I was saying, Habanero, V5, X10, all these things with async and finish provide what I believe is a less cumbersome way to write parallel programs. It has some nice semantics to it that joins all of the descendant tasks that you ever create. So when we made flood fill, we just asynced a ton of tasks that were, children of each other. It just made this huge tree, and then finish just joined them all for us. And so we're going to gain some experience in some of the core features of Java, thread, and executor service. And so to sort of see how that would be built in when I don't have async and finish handy, but also it gives us a chance to use our first thread safe data structure. We'll talk a little bit more about it, the concurrent link queue. We're going to transition very soon into the concurrent part of the project, part of the course. And so we get to sort of deal with a bunch of the problems that come up when you're trying to build something like that. Okay. Some questions that have come in historically on this thing is it more efficient to use threads than to use async and finishes? And my answer to this is not if you did it per task. So there's a huge amount of overhead per thread. The OS is involved every time you create a new thread. This was in some ways the motivation for building Executor Service in the first place, is that what you want to do is amortize the cost if I have a bunch of tasks of creating a thread, because when the thread is done, I could leave that resource up in the operating system and send new tasks at it. So that's what Executor Service and X10 RV5 is doing to try to improve performances using threads underneath and going from there. So let's talk about this a little bit. Thread is the sort of building block that starts it all. It's a heavyweight thing. You're getting the operating system involved to do it. To do this, to have this service, I need the operating system to give me something that I can run something in parallel with other things. That has methods on it like start and join, okay? On top of that, Java eventually in like JDK 7 came around and said, this is too much overhead. We're gonna build executor services that have submit and future get. That's kind of the analogy here. And when tasks we're gonna reuse these threads over and over and over again to amortize or to spread out the overhead cost of creating one of these things. And we're going to provide this for everybody in a consistent way. And then I built V5, which has the sort of async and finish. It's sort of trying to mimic X10 semantics on top of these things, right? And the idea behind these is let's make things a little bit less cumbersome, certainly for an intro to parallel programming class, than executor services. Okay. Another good question is what would the computation graph look like for a series involving threads and executor services look like? Looks exactly the same. I want you to know that computation graphs are sort of applicable across languages and paradigms and all sorts of stuff. I want you to imagine this code where we do statement 1, create some thread, whose runnable would be statement 2. I start that thread, then I execute S3 in the continuation, then I join this thread, and then do S4. This looks just like sort of like the async and finish graph we did before with different things to start it, with different things to async it and finish it. So statement 1 goes, we start the thread. S2 and S3 can now run in parallel with each other. And then we join, which says, oh, okay, well, like make sure that there's this join edge in here so I won't press on to do S4 until both of these things are complete. Or more specifically, this is complete. The normal continuation handles this part. I really like this question. If I'm in a coding, in an interview or a coding assessment setting, would I suggest using using parallelization in this situation? I think this is a great question. Certainly, I would. If I was at a whiteboard, what I would point out is in my algorithm what parts could be parallelized and how, right? So I think that would be a really good opportunity to insert that, talk about the challenge, how you would do it at a high level, but pointing out which parts can be parallel. In a coding assessment, if you had a Java coding assessment and wanted to build it in parallel, I would use executor service. That would be I wouldn't do it in async and finish, right? Like I would do it in executor service. That's sort of the standard Java way to do this. So great question. So let's talk about some of the things that we're going to do. I felt it would have, I'm trying to not make this class too specific to Java, but it felt ridiculous to have an intro to parallel programming class in Java without having students at least make a thread, start it, and join it, okay? And so I provided the links to the Java documentation here of thread. This is sort of the fundamental building block. It's been around since the very beginning so that you could do multi-threaded code or do things in parallel. Thread, this will create a new task, if you will, a very heavyweight one that will, it gives it what to run when things start. This will actually, as an aside, fill in the run method with that target. You can extend thread and override run if you want to do the same thing. And if you called run from the outside, it would do that code as if it was any other normal thing in the continuation, any normal sequential program. If you call start instead, it will get the operating system to give you a resource that can run something in parallel with things, and then that will call run. So that's sort of the async equivalent, is this start. Join is what you can think of as the finish, or the part that says, oh, wait for this thing to complete. And this is the old school thing. I have a picture of Derek Zoolander up here, for those of you who like that movie, like myself. This is the old way to do things. It's still necessary to do things like build the new way to do things. So the new hotness is, and by new, I mean it's a while now, it's since JDK7, is executor service. And this has the ability to submit some task. You could create any number of these executor services. There's a bunch of them. So I think actually, if I go to the package here, going a little off script, if it'll click for me. Yeah, there we go. There's a way in, there's going to be executors, which has a bunch of different ways to create things. You can create cache thread pools, and anybody who's interested in this single thread, you can build a work stealing pool. There's a bunch of different ways to do this. So they're trying to provide a common way to do things in parallel with this, like I said, spreading out the overhead cost. And so they have submit, which is a little bit like analogous to async, or creating a new thread and calling start on it. They have two versions of it. It's unfortunate that they have these two. You can think of this as callable is a feature that returns a value, and you can think of this one as trying to be the one that returns a feature of type void, and doesn't really have a return type. I wish they had only provided this one, but that's a long story. A lot of times, passing a callable type void and returning null is the right choice there, but that may or may not come up on your lab, but just be aware of that. They have this submit, and they also have this invoke all. And like I said, these futures have a function called get to get the result of the computation. So that's sort of the new hotness. And let's talk about one of the sort of programming assignments you're going to have within the context of getting exposed to threads and executor services and future get in a non, X10, V5 kind of context. So first of all, quicksort. Probably a lot of you are familiar with this algorithm. If you are not, there's resources on the wiki, and there was prep on watching how quicksort works. This algorithm has this style where you can build one finish to join them all sort of thing. By that, I mean, some algorithms require that you finish at every level. So one example of this is merge sort. You're going to say, I'm going to go left, you go right kind of thing on doing the upper and lower half of whatever range you're doing. Those two tasks must complete before you combine. Like, there's literally a requirement. You're depending on both of them to go, so that because your merge sort combiner is requiring two sorted sublists, right? So that's something where you have to finish at every level. There's been other examples that have been along the way, like flood fill and in queens, where you're like, well, no one's really depending on these results. I can, for example, flood fill, make as many tasks as I want, just finish before I leave. Or in queens, make as many tasks as you want during search. I'm just going to make sure that they're all completed before I return from this function call. Quicksort is in this category. All the work is done up front in quicksort, so you're actually not waiting on the results like merge sort was. And this gives us an opportunity to tackle some challenges by having one finish to rule them all, if you will, or one the need to track every task that's ever made. Brings up a bunch of challenges that we can tackle in this lab. Okay. Quick note on concurrent link queue, which you're going to need to use in this. It's a wonderful thread safe data structure. A quick note on thread safety. That's a very widely used term. What it basically means is that your data structure is built in such a way that it will be correct, even if multiple tasks or threads mutated or access it at the same time. And so Concurrent link queue is one of these things. Again, when Java started supporting more parallel and concurrent programming, they put in concurrent link queue, its friend concurrent hash map, a bunch of things like this. We're going to use that in this data structure to, excuse me, in this lab to handle any of the data races that would occur when we're adding our tasks to this for the quicksort portion of it. Okay, and with that, let's talk about the join all demo. Okay, and if I look up the concurrent link queue, you'll note it has first of all, it's a queue, and it's a way for us to be able to add things to things. Add a bunch of items to something that behaves like a list, but that's a queue. Iterators, one of the notes is iterators for this queue are weakly consistent. And what that means is it's not going to update its iterator as you go. So if anybody wants to like ask and iterate over all the items in a queue, concurrent link queue is like, I'm not going to necessarily support that well. Okay, it's one way to think about it. So we're going to have to tackle that challenge as we go. I will shoot a separate video on this, the join all demo, because I feel like it's necessary. So I will add that for right now and not shoot this demo now, but just look for that in on the wiki and in our posts. Okay, and like I said, I just covered the weekly consistency. I'm going to encourage everybody to do the join all warm up. It's going to come up handy when you're building your quicksort version. So definitely do that. I promise it'll pay off if you do it. Okay, so let's talk a little bit more about quicksort at a high level. Again, we talked about this exact same graph. This is a Cosgrove proof of proof by picture and PowerPoint, two of the most dangerous proofs of all time combined together. This is how I like to think of the work of quicksort and merge sort. Quicksort does the work up front in partition. Merge sort does it at the end in combine. But we're gonna, you imagine up front, you partition the entire array. And each time so it's n work at the top, there are 2 n over 2 works. Next, there are 4 n over 4 works. After that, 8 n over 8 works. Excuse me, and 16 n over 16 works as far as high as n is. So it's n across. There's log n steps to that. And this is, of course, expected case for merge sort. And so that's where you get the n log n amount of work. The span for a very simple version of quicksort is n plus n over 2 plus n over 4, which is the sort of 2n version. And one of the things I'll throw out there is that there's an opportunity for an optional sort of extra credit parallel. You can parallelize this partition step. Okay, so just like you could parallelize merge sort combine, you can parallelize this step. And I'll leave that as an exercise for everyone to think about. We're going to be covering some of the things that you're going to need very soon. But I'll lead to everybody towards is that all these problems, it's usually really easy to figure out, to operate on every item in parallel. So if you were partitioning and you knew what the pivot was, it's pretty easy to figure out whether you're on the left or right of that pivot. They can all do that independently. The problem is always, where do I write to? Okay, and I'll leave it as an exercise for everyone to think about of how would I parallelize that partition step. Okay, and with that, I will say I'll point you to the wiki and say dig in on this lab and let us know if you have help if you need help, and good luck, have fun.